All right, let's see. Good morning.
Good morning.
It's still morning, right?
Yes, apparently.
Yes. I've been so nice to even bring you people coffee. A whole thing of coffee here, and no one wants coffee. I see how it is.
Do you have the cup? I can pour this out.
There we go. All right. Yes, this coffee is from a box, just like wine. Okay. All right. So uninhibited and inhibited growth and decay models. Okay. This is algebra 3 type stuff. Okay. Super important. Okay. Why is this? Okay. There we go. All right. So okay. Situation in science, nature, economics, and radioactive decay. Population growth, interest paid on investment in which the quantity A varies with time t in such a way that the rate of change A with respect to t is proportional to itself. These situations can be modeled by the differential equation. Okay, so remember, dA dt means that is the derivative of A in terms of time. Yep, very good. Okay, where K is some constant, which is some real number there. Okay, where K is actually going to be greater than 0, that means it's going to be some type of growth. If it is less than 0, which are, what numbers are less than 0? Try again. Negatives, thank you. Okay, decimals are small, okay, but they're not less than 0. Okay? I know, it's okay. All right, so less than 0, negatives means it's decay, so that's going down. Okay? That's important. Okay, so suppose the initial amount A sub naught of the substance is known. A sub naught, it's called A sub naught. Okay, those people that are taking chemistry and all the physics and stuff, A sub naught. Okay, A, the little base 0. Yeah, A sub naught. So that is my initial. Okay, a lot of times you're going to see that where it's going to be M sub naught, it's going to be some T sub naught, it's going to be some sub naught, which is referring to my initial amount of substance known as a given boundary condition or initial condition, okay, where it's A of 0 when t is equal to 0. So that means initial, that is what I'm starting with when time is equal to 0. So I'm always going to have 2 points, okay? I should always have 2 points out of this. Okay, 1 point that I'm going to start off with is at time 0. It doesn't always say time 0, okay? It just says initial amount. So you should know, okay, before I start anything, at time 0, I start with something. Okay, we solve the differential equation where dA dt is equal to k of A by writing it as k dt. Okay, now, if it's written like this, then we integrate both sides of the equation. Integrate. So a differential equation, we're going to integrate. So that means that this one, I'm going to have for dA over A. Okay, if you look closely, algebra happened. We multiply both sides by dt, right? Yes, that's how the dt got over here. And what do we do over here? Divide by A, right? Okay, then we integrate both sides of the equation on the left with respect to A and on the right with respect to t. So we get the formula. So if I start off with this right here, and 1 over A, the integration of 1 over A should give me ln A, right? Yeah? Okay, ln A. Then when I do this, I get k of t, okay, k times t plus c, right? I should actually have a c on both sides, but I'm actually only going to include c on this side over here. Yeah, because I'm going to add it here, I'm going to add it here. You know, I'm not canceling it. There has to be some value. It's like a C1 and a C2, but then I subtract C1 from C2 to get some C3, but I know it's eventually just some constant. Okay? I don't need to do a math on numbers that are hypothetical. Okay? So it's just going to be some constant C. I'm just going to put the C to the right of that. Okay? Does that make sense or no? Yes? Maybe? Yeah. Missy, you good? Okay, good. All right, so right here where A, it's got to be greater than 0. Remember, there's my when I integrate and I get ln A, ln does not exist in the negatives. So that's why I always have to have that absolute value bars there. Absolute value bars. Okay, initial condition right here. Initial condition right here. So it's going to give me this value. Okay, when I do my initial condition, I solve for C. Okay, and it should be ln of a sub naught, whatever that value is. Okay, do the math right here. Okay, if you notice, I keep going to this point. Keep going to this point right here, where eventually it should be down to this, which is my formula, A, which is my amount that I'm going to get and I'm done, right? My output of this. So if I was saying that this is a growth model, this would be equal to the population. So I'm doing this in algebra 4 right now, and I just rewrite this as my output of my population. Then it's going to be times a sub naught, which is my initial. Then it's going to be times e to the kt, where k is going to be my rate of growth or decay. Rate of growth or decay. So if that k is positive, it is a growth. If that k is negative, it is a decay. So now, if I wanted to actually try and find for whatever my population will eventually be, okay, so I plug in my time, right? I plug in my time, I get my population. Okay, I could work this backwards if I want to find the time. Okay, I could work it backwards if I want to find the time. We can. Yeah, I would log it, right? So if I do that, I would actually know my population. So that would be my A over A sub naught is equal to E to the KT, right? Okay, so we're basically coming out over here, right? Okay, at this point right here. So what would I do if I wanted to solve for T right there? Divide both sides by K. Yeah, I would divide both sides by K. So it's going to look like this. So it would be ln of A over A sub naught, all divided by K, is equal to my T. So this is important. I did the algebra for you. If I wanted to solve for time, if I know my initial population and my end population, and I say, hey, when is the population of Phoenix going to finally reach 3 million? Okay, so my end result, my A, would be 3 million. My A sub naught would be my initial population right now. Okay, so I'd have that and that, so it's going to be whatever the growth rate of the city is right now. You can look it up. Whatever the growth rate, there it is growing. So whatever the growth rate is, we would actually have that also at K. And that would give me the time in years it would take for us to actually hit 3 million. Yes? No? Maybe? Possibly. Comprende? Yes. Yes. Das Verdisky. I probably even said it wrong too. That's, yeah. Anyway. All right, so here's the model of growth. Here's the model of decay. Growth goes up, decay goes down. Okay, but now, will it ever go to 0?
No.
Not really. It's usually an asymptote at 0. Okay, that there is going to be some type of asymptote at 0. Okay, now, I got a serious question right here. If we're talking about the population of Phoenix or the population of anything, bacteria, all that other stuff, okay? Okay, so here's one that's quite applicable right now, the coronavirus, okay? There is an outbreak, okay? So there is a growth model of the spread of this right here, okay? Now, it can continually spread, but will it eventually, will it just go up to infinity? No. What is that? What is that called that I can't go any further?
Limit.
Kinda. Okay, it's going to go up to something, but it can't reach it all, right?
Or no, that's
Not asymptote. It's not a math term. Not this math term. It's a science term. You'll eventually get more into it when you get higher level math.
a cap.
Yes, it is a cap, but there's a special name for it. Okay, you guys actually deal with it in biology and stuff like that. It's called the carrying capacity.
Yeah.
So because so if you have bacteria in a dish, right? You have your bacteria in your dish and your population is growing exponentially. Okay? But there is a carrying capacity of that dish. It can only reach a certain point, right? Either there's no more food or there's no more space. So there is a carrying capacity where it'll eventually get you. But the mathematical model that we're looking at is just like this. But that is a differential equation where you actually have two integrals. Because you're going to have an integral of its growth, and then you're also, because over time it's eventually going to hit your carrying capacity, so my growth is going to look like this, but it's also eventually going to start going like this, getting towards some carrying capacity. Okay, it's going to be the same thing with the corona outbreak. So yes, it's going to spread really fast in all the populated areas. Okay, if it ever gets there, but you know what? Now, but then it's going to go really slow to a certain point because you're going to have people like Pacho hiding out in his bunker underground, not talking to anyone. Okay? Yeah, hell no, I don't want to talk to you. Get away from me. All right. So, yes, that's basically it. So, yeah. Anyway. So, you're not going to hit those weirdos that are, afraid of everyone. So, yeah. Anyway, but yeah. Okay. So assume that a colony of bacteria grows at a rate proportional to the number if it doubles in 5 hours, okay, 5 hours, how long will it take for the number of bacteria to triple? Okay, let's give it a value. Let's give it a value. I like throwing in values, okay? I say that it's going to be, my initial would be A, because I feel like that would be, right? And I want it to triple, right? So I'm looking for it to be what? 3A. I'm looking for 3A. I'm looking for 3A, right? Okay. And my rate is doing what?
Growing.
It's growing. It's doubling, isn't it? Okay, so now this one is actually a super easier one too. There's other ways of solving this besides just straight calculus. If you guys remember algebra, it is actually algebra here too. So if I say my initial population was A, I would say I want it to be 3A, and my initial was A, and I have some rate that's going to double, isn't it? Okay. If I wanted to double, how many hours have to pass by? 5 hours have to pass by, right? So that has to be 2 to the first power for it to double. 2 to the first power to double, right? So I can actually do it like this. Watch this. It's going to be, is it hours? Yeah, h over 5. So this one's just straight algebra. So there's different ways of doing it. This is one. It's going to give you an approximation which is really close. Okay, it's not using the E on this one, but this one is really close on this one. Okay, so if I did the same thing, you'll see in a minute. Okay, I'm gonna work this one out, and then we're gonna show what we get. So what would I do here? Divide by 3, right? Or I'm sorry, divide by A, right?
Yeah.
Divide by A, so I should get 3 equals 2 to the h over 5, right? Now what do I do? I'm gonna log it. Log base 2 of 3 is equal to h over 5. Multiply both sides by 5, right? And that's going to give me what? Yeah, it's going to give me the amount of hours it's going to be. So 5 times log base 2 of 3, that's going to tell me how many hours it's going to be. So give me a quick approximation of this, if you could. Is it almost time already? Dang it. What'd you get? No? It is time. I hear the squeaking. All right. Well, okay. If you guys want to work on this, you know, we can finish this up tomorrow too. All right. Don't forget, like, share, and subscribe. Hit that notification, and someone is.